Welcome to day 6 of differential equations. Today we are going to remind ourselves of something we learned in differential calculus, perhaps integral calculus, perhaps Calc BC, but whatever. First, let's recall a fact from differential calculus, and that is if a function is differentiable, then it is locally linear. And what that means is if you zoom in on any differentiable function at any point that it's, or on a function at any point it's differentiable, what you see is that as you zoom in, it looks more and more like its tangent line, to the point where it is, if you zoom in enough, indistinguishable from its tangent line. That means, since the function is differentiable, it looks like a straight line in a neighborhood around any point, and that means we can use tangent lines to approximate it. If it looks like a straight line, then we can use straight lines to predict where the function itself is going. To that end, we've seen before a method of function approximation called Euler's method. I like to tack on Euler's method of function approximation. Often we just call this Euler's method, but if you don't do a lot of function approximating, it's easy to get confused between Euler's method and Newton's method, and be able to distinguish between the two. So this is Euler's method of function approximation. Based on the idea that a function looks like its tangent line if you zoom in enough, and given that you have dy dx is equal to some function of x, or some function of x and y, and an initial value, then you can approximate f using a linearization of f, where we set up the tangent line at that point. That is, we have f of x is approximately the linearization at x naught, which is y naught, plus f of x naught y naught times x minus x naught. And the biggest issue with this is it's only locally linear. The larger you get from your centering value, the more error your approximation is prone to having. So one way we can fix this is just say, okay, well, I never want to take a step size larger than a certain value. Maybe I'm only willing to step 0.1 or 1/10 of a unit, and then I make a new tangent line, and then I go do another 1/10 of a unit, and then I do a new tangent line, and I just successfully follow these tangent lines. So instead of allowing x to change, we're just going to do successive linear approximations. So when we let the next x value be equal to the previous x value plus our step size, this new y value that we get can be rewritten as the old y value plus f of x f evaluated at the previous point, so x and y n. times our step size h. And it goes without saying, hopefully, that our new x value is just our previous x value plus h, right? So these are our equations, which will allow through each step that I take to update what is the new x value and what is the new y value. And then I can continue making those steps. For example, if I tell you I have a function whose derivative is equal to the x value plus 1/2. And I'm starting at an x value of 0. And my function starts at a y value of -1. If I want to estimate y of 2, where this particle, if you will, is at 2 seconds, I can use Euler's method of function approximation. I just have to decide what step size do I want to use. I could let the step size be equal to, I could go whole hog and let step size be equal to 2, right? I'm just going to take one step. If I do that, well, x of 0 is 0. X of 1 is going to be 2, right? I've traveled 2 units down. X of 1 is x sub 0 plus h, and I'm using a step size of 2. My initial y value is -1. So my next y value is going to be y sub 1 is going to be y sub 0 plus f evaluated at the previous point times h. Remember, in our differential equation, we've said y dot is equal to f of xy. So that's what we mean when we say f at the previous value. So y1 is going to be -1 plus, I'm going to go ahead and just move the h out front, h times f evaluated at the previous point, which was 0, -1. This was the previous x value. This was the previous y value, which is -1 plus 2 times. Now f at 0, -1, plugging in 0 for x, I get 0 plus 1/2. 0 plus 1/2 is 1/2 times 2 is 1. And so my approximation for the 0 is, or my approximation for the next y value is 0. But like, if I tell you what the derivative is equal to, you can tell me that the solution to this differential equation is 1/2 x squared plus 1/2 x. And the general antiderivative, the one parameter family of solutions to this differential equation, is 1/2 x squared plus 1/2 x plus c. And then we choose a c so that when I plug in 0, I get -1. When I plug in 0 here, I need to get -1. So that is my actual function. And if I evaluate this function at 2, I get 1/2 of 2 squared plus 1/2 times 2 minus 1. 2 squared is 4. 4 divided by 2 is 2. 1/2 times 2 is 1. And so I actually get a difference of 2. We said that our approximation was 0, and the actual function value is 2. That doesn't seem very good. So let's try a smaller step size, since that's the only thing we're allowed to change in this formula is just how many steps am I taking? Let's try a smaller step size. If I let h be equal to 1, then x0 is 0, x1 is 1, x2 is 2. Y0 is still -1. I'm still starting at -1. Now y1 is going to be -1 plus my new step size is 1. And I'm evaluating f at the previous point, 0, -1. Which is -1 plus f of 0, -1. F is x plus a half. The x value, the previous x value was 0, so it's 0 plus a half. -1 plus a half, which is -1/2. Y2 then is going to be -1/2 plus 1 times f of the previous point now. So I'm trying to make that a little bit more legible. All right, the previous point is now 1 -1/2. X1 is 1, Y1 is -1/2. And evaluating f at this value, remember f was x plus a half. So 1 plus a half is 3/2. And so I get an estimate of 1. So my new estimate is 1. The actual value is 2. I think we can all agree that 1 is a better estimate than 0. But 1 is still not particularly good. So I can make this better. Remembering that y dot is equal to f of xy. In this case, that function is x plus a half. Remembering that x at x0 is 0 and y0 is -1. We're trying to estimate y of 2. We've done a step size of 2. We've done a step size of 1. Let's try a step size of a half. So I'm going to have x0 is 0. X1 is 1/2. X2 is 1. X3 is 3/2 or 1.5. And x4 is going to be 2. So when I make the step size smaller, all I'm doing is making it so that I do more steps, which will make my Fitbit happy. My initial y value is -1. My next y value is going to be -1 plus 1/2 of, now f evaluated at the previous point is going to be 0 plus a half. The previous x value is 0. My function is x plus a half. So -1 plus a half times a half is -1 plus a quarter. -1 plus a quarter is -3/4. My next y value, or my next approximate for the y value, is going to be -3/4 plus my step size is 1/2, and my slope is always equal to x plus a half. My previous x value was 1/2, so 1/2 plus a half. 1/2 plus a half is 1. 1/2 times 1 is 1/2. -3/4 plus a half is -1/4. My next y value is going to be -1/4 plus a half times my previous x value plus a half. Previous x value plus a half. 1 plus a half is 3/2. 3/2 times a half is 3/4. -1/4 plus 3/4 is +1/2. And now y4 is going to be 1/2 plus a half of x plus a half. My previous x value is 3/2. 3/2 plus a half is 2. 2 times a half is 1. Plus a half is 3/2. And so remember, using one step size, we're using a step size of 2, our error was we were off by 2 because we know the exact value is 2 and we got an approximation of 0. With h of 1, we cut our error in half. We know the exact value is 2. We got an approximation of 1. And with h of a half, we got an error of, again, we know the exact value is 2. We got an approximation of 3/2, so our error was just 1/2. And we can imagine, as I get my step size smaller and smaller and smaller, our error should decrease because we're relying on local linearity less and less and less, or if you prefer, we're taking smaller and smaller step sizes, so the function looks more and more like its tangent line over the regions we're looking at. But we have the same problem here that we had when we were using rectangles to approximate the area under a curve, and that is, how good is good enough? All right, if we can do this using arbitrarily small step sizes, at what point do we stop? At what point do we say, okay, this approximation is good enough? Since this won't give us an exact value, it'll just give us an approximation. There has to be some sort of cutoff. To establish cutoffs, we need an agreed upon method of calculating error. We will have 2 forms of errors that we're concerned about in this class. We will have the absolute error, and we will have the relative error. These are the 2 errors we will be concerned about. The absolute error is going to be the magnitude of the actual value minus the approximate value. And then the relative error is going to be the absolute error divided by the actual value. And we don't really care about the sign here, whether it's positive or negative. So I'm just going to put absolute value bars around both of these. Of course, this begs the question, if we know the actual value, why would we ever do an approximation? And that's a great question. On a low level, because the textbook tells us to, and because the test tells us to, but on a higher level, there's no guarantee that we're always going to know the solution to the differential equation. In fact, there are many more differential equations we don't know how to solve than there are that we do know how to solve. Right? Each day we sort of find new differential equations that it turns out we do know how to solve, but there's still whole classes of differential equations that we don't know how to solve. So if we can calculate error, we can tell you how good our approximation is, but often we're not going to be able to calculate the error, at least based on what we know right now. And if the trick to getting a better approximation is just to use more steps, obviously I would want to use as many steps as I can. Like, sure, I could do 4 steps, but why would I do 4 steps when I could do 400 steps? And why would I do 400 steps when I can do 4,000 steps? And I'm not about to sit here and write this out 400 times or 4,000 times. So this is where we invoke some sort of numerical solver. Something that is very good at doing these basic calculations, but not very good at thinking. That is a computer. So we're going to switch to using a computer to help us calculate these things. So let's do the exact same previous problem, but let's invoke Excel to do the grunt work for us. I'm going to include our differential equation, which is the slope is always equal to x plus a half. I need the initial information. So maybe I make a column for n. And then I put my initial x value here. My initial x value was 0. My initial y value was -1. And I need a step size somewhere. So let's say we're going way back. We want a step size of 2. Well, my new x value is just my previous x value plus h. This was only one iteration. My new y value is going to be my old y value plus h times, and now I need to plug in my previous x value to this function. It's x plus a half, my previous x value plus 0.5. And we get our approximation of 0. Our next example, we used an h value of 1. So I need twice as many steps. My new x value is my previous x value plus 1. And my new y value is going to be my previous y value plus h times my function value, which is x plus a half, my previous x value plus a half. And we get an updated approximation. Previous, our approximation was 0. Now our approximation is 1, just like we calculated by hand. Our next h value that we tried was 0.5. I need twice as many steps. And you'll notice because of the way I'm typing this formula in, when I change the h value, I just need to update the h value itself and then do more steps by coding everything in as references to previous cells. I can modify this to do much smaller step sizes relatively easily. So as we calculated with a step size of a half, I get a value of 1.5. Let's cut this step size in half again. I need twice as many steps. And we get a new approximation of 1.75. And we could keep doing this. as long as we wanted to. So let's switch to a slightly different differential equation. Say we have y dot is equal to 0.1 root y plus 0.4 x squared. And we have an initial x value of 2 and an initial y value of 4. And say we want to estimate at 2.5. Obviously, the easiest thing to do here would be to let h be 0.5, just to go straight from where we started to where we want to go. But as we've seen, the larger your step size, the larger area, your error. So that means we need to try to find a step size which is a good middle ground between heavy computation and minimizing error. So let's just say I'm going to use an h value of 1/4. That'll be 2 steps, which is not great, probably. But for a calculation by hand, 2 steps is a reasonable amount. 3 steps is a reasonable amount. 4 steps is a reasonable amount. After 4, probably don't want to do that by hand anymore. So we have x0. Our initial x value was 2. Our next x value then is 2.25 because our step size is 1/4. And our next x value is 2.5. Our initial y value was 4. So our next y value is my previous y value plus h times f up my previous value, which was 2.4. So this is 4 plus 1/4 times f evaluated at 2.4 is 0.1 root 4 plus 0.4 times x squared. X was 2, so times 2 squared, which gives us 4 plus 1/4 times 0.1 times root 4. Root 4 is 2. 0.1 times 2 is 0.2. 2 squared is 4. 0.4 times 4 is 1.6. 0.2 times 1.6 is 1.8. 1.8 divided by 4 is, I don't know, 1.8 divided by 4. So we get 4 plus 1.8 divided by 4. 1.8 divided by 4 plus 4 is 4.45. And my next estimate, my estimate at 2.5 is going to be my previous y value plus h times f evaluated at my previous point, 2.25, 4.45, which is 4.45 plus 1/4 of 0.1 root 2, no, root 4.45 plus 0.4 times 2.25 squared. .25 squared times 0.4 is 2.025. And then the square root of 4.45 is 2.109 times 0.1 is 0.2109. And then add the 2.025 to that. We get 2.236 times 1/4 plus 4.45. We get 5.009. That is our estimate. Again, it's a shame we don't have some sort of software or something that's really good at doing these mind-numbing calculations over and over and over. Okay, so let's switch gears just a little bit. Let's do an example that we can find the exact solution to really easily. The previous example, we didn't have a real convenient way of finding the solution, at least not off the top of our heads. So if we had thought about it, we might have been able to come up with something. So let's say we have the differential equation y dot plus 110y is equal to 100. And x0 is 0, y0 is 2. Let's find the exact solution to this so then we can compare any numerical approximations to that exact solution. And then let's find some numerical approximations. Say we want to evaluate or find the solution to this differential equation. Looking at it, that left-hand side looks like I just need to multiply by some integrating factor. So we will let that integrating factor be e to the integral of 110 x, no, 110 dx, which is e to the 110 x. So this becomes the derivative with respect to x of e to the 110 x y is equal to 100 e to the 110 x. Integrating both sides with respect to x. Gives us y is equal to e to the negative 110 x times the antiderivative of this is e to the 110 x divided by 110. So 100 divided by 110. And so we get 100 over 110 plus c over e to the 110 x. Double checking my work. We started with this. Well, we have an integrating factor of e to the integral of 110. We get e to the 110x as our integrating factor. If I multiply everything by e to the 110x, I get on the left-hand side first times the derivative of the second. So e to 110x times the derivative of y plus second times the derivative of the first. So 110 times e to the 110xy. And on the right-hand side, I get 100 times my integrating factor. So we're good. Undoing the derivative means integrating. That'll give me e to the 110x times y. Moving that over to the other side means dividing both sides by e to the 110x, and then the integral of 100e to the 110x is e to the 110x, 100 divided by 110, plus our constant of integration. And then when I distribute that, the 110x cancels with the e to the negative 110x, so it's reduced to 1, I mean, giving us that. All right, so we know y of 2 is exactly 100 over 110. Perhaps we should find our constant of integration first. Yeah, okay. So we know y of 2, y of 0 is exactly 2, because that's from here. Y of 0 is exactly 2, which should be equal to 100 over 110 plus our constant of integration times e to the negative 110 times 0. So our constant is 2 minus 100 divided by 110. We get 1.091. Now that is an approximation. Maybe we should do the exact value instead. 2 minus 100 over 110. 2 is 220 over 110. 220 minus 100 is 120. I get 120 over 110, which is 12 over 11. So our exact solution then is y of x is equal to 10 over 11 plus 12 over 11 e to the negative 110 x. And if our goal was to approximate y of 3, I get 10 over 11 plus 12 over 11 e to the negative 110 times 3. Which my calculator is pretty insistent is just 0. But that is the exact value. All right, now let's find a numerical approximation for this. And let's use an h value of 0.1. Our derivative is 100 minus 110y. And we have to decide on an h value. Let's just start with an h value of 0.1. So I need a column for n, a column for xn, a column for yn. We started at an x value of 0 and I'm going to 3. So I need a lot of iterations. Not that many though. I only need 30 iterations. It's almost like I could have calculated that beforehand. my initial y value was 2. And my next y value is going to be my previous y value plus h times, and now I'm evaluating my slope. I'm finding my slope at the previous point. So 100 minus 110 times the previous y value. So our estimate here is 1.1 times 10 to the 30th. This is clearly problematic. Let's double check to make sure I didn't type anything in incorrectly. I get 100 minus 110y. That part's good. Here I get 100 minus 110 times my previous y value. So we're bouncing wildly between these values. Let's try a much smaller y value, or a much smaller step size. Let's try 0.01. Let's do 0.02. Still oscillating wildly. This makes us wonder if maybe that's not a glitch, but a feature. Perhaps the solutions here just oscillate wildly. Although if we look at the behavior of the function, based on what we understand about parent functions, that should not be the case, because this is just an exponential decay function. And what we have here is exponential growth. So clearly there's something else going on here. That means that while Euler's method of function approximation is a powerful method to approximate, that just means we need to use Euler's method carefully. Right? We need to perhaps do some more research to find out what is it that's making this behave wildly in certain situations. All right. I'm going to give you a new definition. And this is just because your textbook is going to use it, so you need to know what it means. The function ERF of x is simply defined as 2 over the square root of pi times the integral from 0 to x of e to the negative t squared dt. So if we ever see this pop up in a solution, we know that this doesn't have a closed form solution. And so we can't find the antiderivative here. We don't know the antiderivative here. So if this pops up, we can just simplify it as ERF of x. I prefer to think of this as the integral from 0 to x of e to the negative t squared dt is equal to root pi over 2 times ERF of x. That way, anytime I see the integral from 0 to x of e to the negative t squared dt, I can just swap it out 1-to-1 for that. I don't have to try to get the 2 over root pi to appear. We might see this show up if we're asked to solve the differential equation y dot minus 2xy is equal to 2. We have tools at our disposal to find the solution to this. We can just use an integrating factor. Here, e is equal to the, mu is equal to the e to the integral of negative 2x dx, which is e to the negative x squared. So this is the derivative with respect to x of e to the negative x squared y is equal to 2e to the negative x squared. And now, if I try to undo that derivative, I get e to the negative x squared y is equal to the integral from 0 to x of e to the negative t squared dt times 2. Plus some constant. So y then is 2e to the x squared times the integral from 0 to x of e to the negative t squared dt plus c e to the x squared. And so if I wanted to estimate, let's say we're given the point when x is 0, y is 1. When x is 0, y is 1. Well, if x is 0, this is the integral from 0 to 0. So this whole term goes away. When I plug in 0 for x here, I get c, and I need that to be equal to 1. So plus 1 e to the x squared. And this can be written equivalently as 2e to the x squared integral from 0 to x of e to the negative t squared dt is that. So this is 2e to the x squared times the integral from 0 to x of blah, blah, blah is root pi over 2 erf of x plus e to the x squared, which is e to the x squared times 1 plus root pi erf of x. And so while we couldn't get rid of the integral in our solution, we can at least make it look pretty by using erf of x instead of an integral. Now, if I were to ask you for the exact solution at any value x except for 0, we're going to be unable to do this because at its heart, this needs a numerical approximation. So no matter what we want, no matter what we do, if I were to ask you what is y of 1, you're going to have to give me a numerical approximation. It's up to you if you want to give the numerical approximation using Euler's method of function approximation given the derivative, or if you want to approximate integral using rectangles or triangles or trapezoids or whatever. All right, this was video 1. I will see you on video 2.